All right, so this is section 4.2, real zeros of a polynomial function. Now this is going to be a little bit frustrating because we are going to look at possible solutions, possible real solutions, and we're going to list all of those things, even though we can technically find the exact real solutions. Just work with the process here. I promise. It'll all come together, but it might be frustrating right at the beginning. So section 4.2, the real zeros of a polynomial function. First learning objective is to use remainder and factor theorems. So we need to know what the remainder and factor theorems are. So if f of x and g of x are polynomial functions, g of x has a degree greater than 0, then there are unique polynomial functions q and r such that when I divide f of x by g of x, I get q of x plus my remainder divided by g of x. So this is just like long division. When I do division, I have, if you remember back when we did long division, we do our, what we get, our number we get, whole number we get, plus our remainder over our original value. That's all this is saying, but it also applies to polynomials. So if f is a polynomial function, and f of x is divided by x minus c, then the remainder is whatever value you get when you plug c into your function. So if you're dividing by your polynomial by x minus c, then your remainder will be whatever you get when you put c into your function. So let's see how that applies. We're going to take x cubed plus 3x squared plus 2x minus 1 and divide it by x plus 2. So we are going to put in negative 2. Why do we use negative 2 and not positive 2? What do you think, Josh?
Because x plus 2, you switch the signs.
Because if you look at our remainder theorem, it says x minus c. And in order for c to be a positive, or in order for it to be a positive here, it needed to be x minus negative 2. So we put in the opposite of what's next to our x. So when we do that, we get negative 1. So the remainder is negative 1. The next one, we put in positive 1 because x minus c, our c is 1. And when we do that, we get a remainder of 5. So it's pretty easy to find the remainders. You just plug in the opposite of the number you're dividing by. Okay, this is the factor theorem. If x minus c is a factor of your polynomial, then when I plug c into my function, I should get out 0. Totally makes logical sense. So f of c equals 0, then x minus c is a factor. If x minus c is a factor, then f of c is 0. So you can use it both ways. Let's see how that looks. So we're going to determine whether x plus 1 is a factor. So I'm going to put in negative 1 and see if I get out 0. So I plug negative 1 into my function, and I do get out 0. So yes, it is a factor. I'm going to put in positive 1 because x minus 1, the c is positive. And I get out a remainder of 4. So no, x minus 1 is not a factor. All right, a polynomial function cannot have any more real 0 than its degree. So if I'm 5th degree, I can't have any more than 5 zeros. If I'm 4th degree, I can't have any more than 4 zeros. So whatever your degree is, you can't exceed that amount of zeros. Easy. The next learning objective, we're going to use the rational zeros theorem to list potential rational zeros of a polynomial function. So these are just possible zeros. So if I have my polynomial function where the coefficient is an integer, if p over q in lowest terms is a rational zero of f, then p must be a factor. So p over q is a rational zero. Then p must be a factor of my last term, and q must be a factor of my first coefficient. So we're going to start looking at factors of my last term and factors of my first coefficient, putting the last over the first, and putting together possible rational zeros. So in this polynomial, we're going to look at factors of negative 12 and factors of 3. We're going to put these factors over these factors, and it's going to be a whole list of awesomeness. So on your paper, I don't believe that this is on there, so can you guys write that in? Factors of the constant over factors of the leading coefficient, and you're going to list all the different possibilities. So factors of the constant are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus or minus 6, plus or minus 12. Those are all the factors of 12, and you have to include the positives and negatives, because if your factor is a positive 1, then negative 12 can be its buddy, and if your factor is negative 1, then positive 12 can be its buddy. So both positive and negative are options. Thankfully, the factors of q are less, so we look at factors of 3 are 1 and 3, and we have to include the positive values of 1 and the negative values of 1, and also 3. So we put all those together. So 1 over 1 is 1, and it's positive or negative. Then we got 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. Then we've got 1 over 3, 2 over 3, 3 over 3, we already included that. 4 over 3, 6 over 3, that's 2, we already did that. And 12 over 3, that's 4. So you don't have to list the repeats. If we already had 4, you don't have to relist 4. You have to list the positive and negative versions of each of those. So tons of possible solutions, but at least better than a million, infinitely many. So that's how you list all the rational zeros, all possible rational zeros. You're not even narrowing in and finding the actual zeros. You're just listing the possibles. And if you're okay with stopping there, being okay with that, then you'll do fine on that section of the quiz. Okay, so now we're going to find the real zeros. So we need to factor our polynomial if it's possible. So we're going to use the degree of the polynomial to determine the maximum number of zeros. Third degree polynomial, maximum number of zeros is 3. There are at most 3 real zeros. Okay. If the polynomial has integer coefficients, we're going to use the rational zeros theorem to identify those rational numbers that could potentially be zeros. Then we're going to use the factor theorem to plug in each potential rational zero until we find one that works. We're going to repeat the steps until you've tested all the zeros and have all the zeros for your polynomial. So we find that negative 1 is a 0. So when you plug in -1, you get -3 plus 8 is -5 plus 7. Sorry, hold on. 8 -3 is. So when we plug in 1, I'm not sure why they're doing synthetic division here. I get that. Once you find the factor, so once you find that -1 is a factor, you use synthetic division. Okay, so you use synthetic division to divide out your factor once you find it, or your 0. And you get x plus 1 times 3x squared plus 5x minus 12. You can factor 3x squared plus 5x minus 12, x plus 3, 3x minus 4. You set those equal to 0 to find your zeros, and you get that there is a 0 at -1, -3, and 4/3. So use the degree to determine the maximum number of zeros. Use rational zeros theorem to give you your possible. Once you find your potential, use substitution, synthetic division or long division to test each polynomial. Each time a 0 is found, repeat step 2 so you can get it down to a factored polynomial. Let me pause.